we go. So thank you, Cris, again. I'll
cool,
let you.
great. Thanks, Gianluca. Thanks for inviting me. Good to be back, and you completely took my first slide, so that's fantastic. So I just put together a bunch of slides about my work from the last 5 or 6 years at Nvidia, and it's actually kind of a contiguous story. I have not done the typical tech engineer strategy of spending 2 years at a company in Silicon Valley and then jumping to the next company and starting another project. I have been at Nvidia was my first industry job, and it's my current industry job, and I absolutely love it here. And I just want to go through some of the evolution of how I think about some of these problems and what problems I think we can solve. So first, who am I? Like Gianluca said, I'm not going to, he did a great job. I'm not going to focus on this. Yeah, ICMA alumni from 2011, worked with Eric Darve on fast multiple methods, moved to IACS to boot up the Applied Computational Science. Was a new institute that I helped boot up and write the core for and see through the first couple of master's classes for it. And now I'm in Nvidia Research. And Nvidia Research has a really interesting story. A lot of products aren't supported by Nvidia Research, at least the group that I'm in. But a lot of products originate in the group that I'm in. So for example, you might have heard of Thrust, you might have heard of Cub. CUDNN is almost ubiquitous in AI and deep learning computing. CUSP for sparse algorithms, Cutlass for dense linear algebra algorithms, Legion and Leagate has seeped, I've seen it in a lot of grad student projects recently. We do a lot of compiler work and memory model work as well. Our work has even gotten into the C++ standard itself. Jared Haberach is one of my heroes, and he's a coworker of mine and does a lot of really, really solid C++ work that is actually standardized now. And I think that is really amazing to influence the entire language so that we can use it better for high performance computing. So I threw together this talk as kind of a conglomerate. I threw all the slides into a big pile and then figured out which ones I wanted to use. But this is pretty much compiled from a bunch of talks I've given in the past 5 years at Nvidia. So you can find these, if you're looking for more information, you can find these at Supercomputing 2017, GTC 2018, Bliss 2019. NTech, this is a private internal technology conference that we have at Nvidia. But I'm going to tell you a few secrets, but not everything. And I hope I'll be okay. So my PhD again was on hierarchical numerical algorithms, and this is actually on my website right now. So that includes things like H matrices, tree codes, generalized n-body problems. It's got a very, very rich literature and a very, very rich structure. There's lots of variants of these types of algorithms, and there's lots of ways to exploit structure in dense matrices, and that's what I really, really like. And that's the way that my career has been following for the last 10 years, is looking for structure and exploiting it. And structure can come in a lot of different forms. It can come in low rank structures, it can come in symmetries of the problem that you're working on, it can come in computing strategies, lots of different forms. And then as just kind of a teaser, my favorite and everyone's favorite structured dense algorithm, I think, is the Fourier, the fast Fourier transform. This is kind of the ultimate structured dense matrix, and it has so many beautiful symmetries and coincidences that aren't actually coincidences. And it's the most famous version of a structured dense algorithm because we never actually evaluate elements of this matrix, but we still apply it implicitly all the time. And it has this fundamentally hierarchical structure that is inherently recursive. But it also has this interesting low rank structure that fewer people know about. And it's not a classic fast multiple low rank structure. It's in a different class of low rank structure, but it turns out you can still exploit that. But in order to tell you that story, I have to tell you another story. And this story started out when I left academia, when I left Boston. I lived in UC Irvine for almost a year. And who happened to be at UC Irvine at the time, I was looking for someone to collaborate with. I was looking to start, I was working at Nvidia. They were allowing me to work remotely. But I was at the university, so I thought I would look for collaborators and problems to work on and some help. So who do I bump into? I bump into someone that might be familiar to a lot of people in this group. It was Professor Anima Anand Kumar, who recently actually joined NVIDIA, I think 2 years ago. And she is now a professor at Caltech and and the lead research scientist for oh shoot, what's her actual title? I don't know, something AI, something. And she came to me with she and her students came to me with problems they wanted to do fundamentally tensor operations in AI. And I'm like, oh, that's a cool problem. And you know, all of our data is inherently multidimensional now, and we want to work on that inside of AI. The fundamental operation on tensors is tensor contractions, which are the immediate generalization of like matrix-matrix multiplication, which is one of the fundamental numerical algorithms that we all use already. So this seemed pretty attractive to me. It was a core primitive of multilinear algebra. It has Blaz level 3 compute intensity, so you should be able to achieve what we at NVIDIA call speed of light. Everything is measured against the speed of light, which is the theoretical speed of the actual GPU. So if you are getting 99.99% the speed of light, you're good. If you're getting 95% the speed of light, then you go to my coworker, Dwayne Merrill, who will like take it apart by hand and program with a lightning bolt, you know, for that last 1%. And he's absolutely incredible. But the point being that we measure everything at NVIDIA against the speed of light. And the problem is that there was nothing for Anima to use for tensor contractions. And initially, I wasn't actually interested in this problem. I understood it, but I had other fish to fry. I wanted to go back to this Fourier problem. I had my sights set on the Fourier problem. However, something happened inside when I was working on the Fourier problem. I was able to cast it to all of these tensor contractions. So I went back to Anima and I said, yeah, I need tensor contractions too. Let's work on this together. And the fundamental problem with working on tensor contractions in GPUs and CPUs for that matter, is that all of the tensor contraction libraries that you find transform the tensors into a matrix-matrix multiplication, which means that what they end up doing is they spend a lot of time transposing the tensor and folding it into a matrix. And you can see how much of that time is actually spent doing the transposition as a function of the problem size here. So because the GPU has so much headroom from its compute to communication ratio, for small sizes, you're almost doing everything on the GPU in just doing this transposition stage. But if you do a large enough problem, you can almost tolerate it at like 20% of the time here. But again, that's very far off from the speed of light, which would be 0 right here. CPUs, we don't care about them too much, but yeah, they're pretty bad too. You're wasting half or more of your time just doing memory motion and not accomplishing anything useful. So which tensor contractions can be evaluated with existing Blaz algorithms, which claim to achieve the speed of light for various architectures. We have cuBLAS, we have CPU Blaz implementations in MKL and Bliss, etc. And it turns out how many, this is 8 out of 36 tensor contractions of order 3-2 can be evaluated with a single gem call at the speed of light. So you're getting not a large subset of this problem space. So one of my very first projects at NVIDIA was, hey, how do we solve this in a way that looks like cuBLAS, that the engineers can actually implement, and that would be of most use to our use cases. And so I proposed this cuBLAS gem-strided batched function to be added to cuBLAS. And it turns out that this was very easy to implement. I was actually able to reach inside of cuBLAS and provide a prototype to the engineers. They did much better than me, but I was still new. And it's extremely complicated. We had this pointer-to-pointer batch gem that existed already, and that was already available in MKL and cuBLAS. So this wasn't too much of a stretch for them. They were able to implement it really quickly, and they were able to get really good performance out of it. But the point being that we were able to get SOL out of this. So it performs almost exactly on par with the normal gem that you would expect. So no surprises there. There's no pointer-to-pointer weirdo data structure or overhead. Everything just acts exactly like you're calling a normal matrix multiplication, and you get a lot more coverage. These are all the third-order tensor times second-order tensor computations that you can perform with just gem and strided batched gem. So we got a lot more coverage, which is fantastic. But you still see these outliers, which we can't evaluate, and there's certain reasons for that. Which I had to grapple with for a few years. But ultimately, I had this kind of thing in mind, where I would love to have a general tensor contraction operation that operated on GPUs, dispatched to something like batch gem or outer product or diagonal matrix multiplication or gem V, what had you, figured out the right implementation. In general, this is called the LAMP problem, the linear algebra mapping problem. But then for higher order tensors, of course, would dispatch to some kind of generic tensor contraction engine. Now, why did I want that? Because in parallel, I was actually working on the fast Fourier transform. And so when I brought some of this hierarchical methods work to Nvidia, some of my friends immediately said, well, the Fourier matrix is a highly structured dense matrix. Can you do anything there? And it turns out that you can. I knew about some of these techniques, but I did not think they could work. But now I'm going to show you how they actually work. So this is the implementation of a one-dimensional FFT. It involves 3 transpositions and 3 stages of compute. And this is what the profile of those look like when you run it on 2 GPUs. And so the yellow here is all memory motion. Again, same kind of story as in the tensor contractions. We want to spend as little time moving memory around and as much time doing useful computation as possible. And it turns out that computation is mostly more or less free, and moving memory around is almost always the expensive part in any serious computation. So we want to avoid these transpositions. Edelman, in 1999, wrote down a very, very interesting algorithm, which can be viewed as just a different factorization of this Fourier matrix. And this is cool because I had never seen any kind of like really, really unique, solid alternate factorization of the Fourier matrix. I mean, everyone uses the same, Cooley-Tukey algorithm, which Euler wrote down, I think, 300 or 400 years ago. And it's been the same algorithm ever since. But this one does something very, very different. It has this weirdo block diagonal matrix. And if you just did a direct application of this matrix M, then it would destroy the asymptotic complexity. You would no longer be n log n, so obviously it wouldn't be competitive. However, each of these C matrices here is a dense kernel matrix, and it happens to look like this weirdo cotangent matrix, and it has some bonkers properties. One, it can be viewed as a fast multiple method where the source and targets are the integers. It's periodic. You don't see a lot of periodic fast multiple methods, but that's interesting. It's distributed because we're fundamentally doing a distributed fast Fourier transform. Each one of these is m by m, but there's also p of them. So we have to do many, many, many fast multiple methods at the same time, and they're all interleaved. So you don't even have all of them in the same place. They're all distributed. And so I started sweating when I saw this. I'm like, there's no way this is gonna work. But I did some, napkin math, and it came out close. And I knew that the computation to communication ratio was very high for GPUs and was going to continue to go higher. So I'm like, all right, if this doesn't work now, which it probably won't, then I'm going to bet that in 5 years it probably will. So I'll go ahead and work on it now. And so first I made some interesting observations. So we need to compute P-1 distributed fast multiple methods of size m by m. And then these last 3 stages actually change the one-dimensional FFT into a two-dimensional FFT. And theoretically, that's just gorgeous. This M matrix is a transformation object to transform a one-dimensional FFT into a two-dimensional FFT. And two-dimensional FFTs only require a single transposition. So if you write me a faster 2D FFT, then I can make all your 1D FFTs much faster. So this was the key then for the fast Fourier transform, which was and this is what brought me back to Anima to work on the tensor contractions as well, is that I was able to translate every stage of the computation of this FMM into a series of tensor contractions. So all of the red stages here are simply calls to this Kubla's gem-threaded batch, which I wrote with Anima's group. And this made it into Kubla's. So that means that almost all of the stages are going to be executed at the speed of light. We have 3 communication stages in between here. And those communication stages are pretty small, so I should be able to overlap them with computation pretty well. And that left 2 stages, and that left 2 stages that I had that didn't fit into this tensor contraction. These were the holes in the previous table that didn't fit into this gem-threaded batched formulation. So I did have to write 3 custom kernels by myself in order to do that. And now if we look at the same kind of profile, we have the normal fast Fourier transform here, which is doing all of its communication. And down here we have our FMM accelerated FFT, which is doing a heck of a lot of compute. And then this side is all of the two-dimensional, the 2D FFT, which could obviously be better. But I'm doing a pretty great job of overlapping the communication and computation. And you can see each stage of the computation here being launched. And this blew my absolute mind when I saw it the first time, because I realized that I was doing 255 fast multiple methods of 500,000 by 500,000 each, all in 32 microseconds on, I believe this was a Pascal. Yes, this is a P100. And that blew my mind because I had never thought that would have been possible in grad school when I was working on fast multiple methods in grad school. So what does the actual performance look like compared to a normal FFT? Well, if you look at it on a K40, which 4 years ago, were still pretty common, I was only getting about 4% improvement, a 5% improvement for the long tail out here. And for the short tail, some weird things were going on, and 75% to 80% improvement, which is not bad. But just like I said, I thought this was going to get better, and I had the Pascals available to me, and of course, in the jump from the Kepler to the Pascal architectures, again, this jumps to about 30%, so that was promising, but still not absolutely groundbreaking. If we move to 8 Pascals, it does scale over multiple GPUs pretty well. Now all of a sudden we're 100% faster, so 2.1x on 8 Pascals each. But right when I released so the story is actually that when I was working on this, the Pascal architecture had not been released yet, and we did not have these clusters yet. So I initially saw the results on Kepler and saw 4 or 5% improvements, and I'm like, I don't know if I want to publish this. This is not fantastic. But inside that same month, we released the Pascal architecture, and I saw the 1.29, and then we also launched our first DGX boxes of the 8x Pascals, and I was one of the first users of the DGX boxes, and this was one of the first applications, and this was certainly highlighted at GTC, which was absolutely fantastic. And then of course, if you go to the new Voltas, these should be Volta. These are the wrong plots. Anyway, so if you test this, these are absolutely the wrong plots. If you test this on the Volta architectures and the new Ampere architectures, you have a maximum 3x speed up. I'm getting 2.9, 2.95 now. It's pretty fantastic, and so that intuition of, oh, I should do this research now, and if it doesn't work now, it'll work in 5 years, was very good, and I had very good timing with that, so I got pretty lucky there. As you can see, a lot of the computation is being performed inside of the batch gem. That's all of this red here. So if I didn't have that previous work on the tensor contractions, then this wouldn't have been a success, I believe. And it has a lot of nice properties, and I actually want to return to the FFT in the future. But in order to return to it, I need even more complicated tensor contractions, and that's kind of where I got stuck for a little while. So I want to take you through more of the tensor contraction stories first. So after the FFT project, I had a lot of ideas about how I could use this new tensor power in AI for other FFT calculations and for other numerical problems that I was interested in. And so the obvious one was to look at tensor contractions for AI, and this was also a strong collaboration with Anima, who again later joined Nvidia, and then I kind of let her do this work instead of me because she's going to do it better. She has much more experience in the applications of tensors with AIs than I do. But I did this as an excuse to learn more about these applications and learn more about what the problems were with actually writing these tensor contractions. I still had a dream of being able to execute any kind of dense linear algebra I wanted on a GPU, but the problem was, at the time, no one knew how to write those kernels. And so in the AI community, they have this really nice notation for tensors, which I really liked. And you get to draw all these pretty pictures that denote vectorization and matricization and tensorization of these matrices, vectors, and tensors. You can express inner products and outer products and SVDs with all of these nice images, and you can talk about these fancy like generalizations of SVDs for tensor contractions, which some of you are certainly familiar with. This is the CP decomposition, and you can draw it kind of like this. Of course, it has a lot of nice properties, and you can use the CP decomposition to compress various levels inside of any kind of deep learning network that you're interested in. The Tucker decomposition is very similar to the CP decomposition, and you can write an algorithm using this kind of notation, which is it's pretty. It takes a while to explain, but it's pretty. I started looking at tensor ring decompositions. This actually has a lot of connections to kernel methods and hierarchical decompositions, which is why I was interested in it. There's this really subtle, interesting connection between this and a lot of physics problems. And so it applies directly pretty well. This is actually my favorite decomposition that's used inside of AI. If you have a matrix or a tensor, the Kronecker decomposition is fantastic because it it preserves a lot of properties that you might be interested in embedding into your deep learning system. And I have a lot of opinions on that. I think that's the future of how we design deep learning systems, is learning how to embed symmetries and preserve certain properties of the numerics, and then casting our problems in terms of that. But that's another discussion. The Kronecker decomposition itself preserves numerical properties of the matrices. And so if you wanted to build a unitary transformation inside of your deep learning network, but not express the entire large matrix or tensor, and try to keep that unitary, you chop it up into little pieces with the Kronecker decomposition, keep all those pieces unitary, and then you can guarantee that the net result of that operator is still unitary, which are very nice properties to have. And then of course you can have really, really exotic decompositions, and you can imagine the numerics. You can understand why people draw these images, because writing down the Einstein notation and the summons for all of these gets really, really, really messy. And having some way of evaluating these on high performance machines is actually one of our priorities right now. And there's a lot of discussions about how to do that internally at Nvidia. And so we can construct really rich structures with these, and the goal being to reflect any kind of a priori knowledge that we can take advantage of inside of the deep learning network. So I worked on that for a while. It kind of became a zoo of these decompositions that you could apply without a lot of rhyme or reason. For doing so, everything just kind of seemed to work if you massaged it enough. You know, everyone has that joke of how many grad student hours did that AI research take. And so that's what it felt like. But I tended to hone in on another problem, which is that problem that I've alluded to this entire section of how the heck do we evaluate these kinds of operators? That evaluate the decompositions, perform these tensor contractions, and actually try and get some kind of guarantee that these programs will run with any sort of compute efficiency. And that is a difficult problem. And some software libraries like TensorLi, written by Jean Cosifi, who also recently joined NVIDIA, try to support a lot of these tensor operations. But again, where this is lacking is that some of the kernels simply don't exist to evaluate these operations on GPUs. And so there's a lot of resources, but writing these kernels became a big bottleneck. So I started thinking very, very deeply about how we currently write software for dense linear algebra and how we want to write software for dense linear algebra, and what problems that would solve. So what existed is Cutlass. An interesting backstory of Cutlass is that it also originated in Nvidia Research PSA, which is my group. Dwayne Merrill asked the question something like 4 or 5 years ago: what would it take to write a speed of light gem matrix multiplication in CUDA? What would it take? And so he wrote a speed of light gem in CUDA and found that the problem wasn't really CUDA, it was the compiler. And he spent a very, very long time tweaking the compiler to the architecture so that the compiler would do a much better job of compiling these kernels. In the process, he did have, you know, a library of CUDA kernels to implement some of these matrix multiplications, and that's what eventually became Cutlass. Now Cutlass has grown into a C++ template library for, it claims it's for deep learning. It's for dense linear algebra, and it aims to help you program matrix multiplications and convolutions and all of this dense linear algebra all the way down through the hierarchy of the GPU. that's its goal. It does a pretty good job. It has very good coverage of all the operations that you would want to perform. However, if you have any experience with trying to take it apart and any experience with trying to hack on it to do even the slightest little skew, this is where I started with trying to write tensor contractions. It's nearly impossible to hack on. There are an insane amount of assumptions that go into every single level. Here, you kind of have to have a full stack knowledge of everything that's going on. And it's kind of a bad world to live in. Even the experts don't understand very large portions of the library. I'd say that's kind of fair. But the goal is valid. I'm sorry, I'm spacing on the word. That's weird. The goal is a nice one to have. We would like a way to organize data and threads in a way that is comprehensible and versatile and composable. These are the basic software principles that we would like to have. And it is a very good attempt at doing so. And the other one that I was involved in starting was CU Tensor. Nvidia hired Paul Springer, who had basically done his PhD on writing tensor contractions for CPUs and GPUs. And Nvidia hired him, and he spearheaded this library called CU Tensor. And so he and I had a lot of discussions about how to write this. But this supports, all of the BLAS hierarchy, and it supports pretty much any tensor contractions, any tensor contraction that you throw at it. So plain Jane outer products, batch gems, like we've talked about previously, single mode and multi-mode batch tensor contractions. And a lot of these kernels were initially written by hand, and then Paul started using Cutlass. And bumping into some Cutlass things, but the interface is completely reasonable. You pass it a descriptor of your tensors. It can perform the contractions. It can hopefully take advantage of tensor cores if it's available on the architecture that you're using, et cetera, and it performs very well. You'll notice, well, I won't say that. So this is a good library. I thought that the way it was implemented, I wanted to be more careful about how it was implemented. And I had a vision from all of my previous experience in working in tensors. I had a vision of how I believe it should be written. And that is what I've been working on for the last 2 or 3 years now. And so this is going to be a taste of that. I can't talk about it all, but because we're trying to do tech transfer right now and we're trying to write papers on it right now, but I'll try to give you a flavor. So back to the goal. The goal is to organize data and threads and then be able to compose them properly. And this gets really complicated. These layouts here of threads are not just row major or column major. Everyone's familiar with those kinds of layouts. These are not those layouts. This thing is even more messy. It takes a lot of bookkeeping to keep track of where everything is and when it is, and which threads. Each color here is a different thread. And so it's, this is all booking. This layout is also kind of strange. It's not, again, it's not row major, column major, and it's even worse than that because this layout is a layout of these layouts. So each one of these blocks is an entire block of these 4 guys. So this gets insanely messy, and this is what's implemented all throughout Cutlass if you dive into that code. And that's why it's so hard to hack on, because you have to know all of these things about everything. And then this layout isn't even rectilinear affine. This is called a Swizzle Layout. It's even messier for certain reasons. So ultimately what I wanted is I wanted some concept of a layout that I could construct that was powerful enough to represent all of these things, but also be strong enough to be able to manipulate. So I wanted to create layouts of layouts and, you know, construct like an algebra of layouts. And that's kind of exactly what I did. So I found a unifying representation that was actually based on Tensor, Tensor folding, and say, all right, a layout is any function from a coordinate space to what I call an index space in memory, where I can look up the data at that coordinate. And so with that, then I can just start defining these functions that represent a row major layout, a column major layout, a padded layout, or even a mixed. This is some weird interleaved plus padded layout here. But you can't stop there. So this isn't particularly unique. It's not particularly interesting either. But if you go a few steps further, then you can actually create a literal algebra of layouts, and the fundamental operation being functional composition. So this is kind of an extension of the symmetric group. So I call this the logical product. This is literally taking the product of two layouts. I want to produce a layout where every element of B is a layout of A, and it will give me a new layout. So I can construct these atoms, these layout atoms, like I showed on the previous slide, and then take the product with another layout to produce a layout of layouts. And it's going to keep track of all the bookkeeping for me here, so I don't have to. Furthermore, logical divide will kind of like unfold a tensor. And so if I want a certain subtensor view of those along some mode, then it'll find out it will figure out the layout of the alternative residual modes. You can do some really, really fancy stuff with this, and because it really is an algebra, I can be really, really formal about the construction of all of these operators, and I can parameterize all of these very, very different partitioning patterns. And once you parameterize these, and you have this algebra that you can manipulate, all of a sudden doing partitionings of data. We can use layouts for very complicated layouts of data, and then layouts for very complicated layouts of threads, and then effectively divide one by the other, and that's a partitioning. And I don't particularly care about which layout each one of those are. I can compute that partition, and I can parameterize these different partitioning patterns here as well. So what do we get for that? We get this really amazing programming system that lets us take projections and partitions of all of these threads and data and produce subtensor views, which are, again, not moving data around, but just giving us a view, a subtensor view of the original data for our particular thread. So if I wanted to write a gem, my new interface would look something like this. And then I would partition the A, B, and the C data against my layout of threads that I have here, and get subtensor views of all of these. Now, what do we do with those subtensor views? Well, you can do anything you want with them. We could just compute the matrix multiplication directly using the really boring triple for loop that we all know and love. This is nice to have. Of course, inside of GPUs, it's a little more complicated. We can write this, but in order to get speed of light performance, we need to write it a little bit more carefully with pipelining of shared memory, pipelining of registers, some even fancier stuff that I can't talk about. So this would be a pipeline, a shared memory pipeline here. So I'm computing on one tile at the same time that I'm copying the next tile into memory. So I'm overlapping the compute and the memory motion. And the really cool thing about this is that these are computing on tensors. They don't have to know about the thread layouts, data layouts. It just takes the tensor, which knows about where all of its memory is, and it's able to reason about this. And so the copy algorithm, for example, will be able to inspect the layout. It'll perform compatibility checks to make sure you're sane and doing something that makes sense. it'll auto-vectorize loads and stores. So instead of loading 4 int 32s, it'll combine all 4 of those int 32s into a single 128-bit load, which is simply more efficient on the instruction cache. And it also knows about architecture-specific memory operations. So it'll dispatch to fancy like LDGSTS, if you're familiar with that, or LDSM, or anything that we build into our next generation of GPUs. And it's doing all of that under the hood right now. Similarly for GEM, compatibility checks, pipelining and register banking and reuse patterns, it knows about those, and it can inspect the layouts of all of these and actually reason about them. And again, if you have Tensor Core units, it can detect that and use them if it's possible, which is really, really fantastic. And you don't sacrifice anything for this. All of a sudden, I can program a speed of light matrix multiplication in just a few lines of code. But Cris, this Tensor Core you showed me is really, really complicated. There's no way you can do the same thing. You just showed us a single, element here, right? These are single elements. You're accumulating them. There's no way you can do this Tensor Core stuff in the same way. So this is yeah, you caught me, right? I'm doing a single element matrix multiplication here. I'm partitioning the matrices against the single element. And in order to do a Tensor Core gem, I have to change the code to use from a single element to use a Tensor Core. This is my Tensor Core object here. It knows about all of these layouts, and so when you're doing this partitioning now, each one of these blocks, each one of these little blocks here is this Tensor Core subpartition. And this is just implemented with functional composition, and it's very formal and provable, and I can print this stuff out at every single stage. And it's very hard to write a matrix multiplication that's wrong, which is the way I want it to be. I can write WMMA. If you're familiar with WMMA, its performance sucks, and I hate it, and it shouldn't have been included in CUDA. I can write WMMA in here, and it's actually better than the one that's included in CUDA. And so then I can write speed of light Tensor Core matrix multiplications here for any type that you want, for any transpose system that you want, etc. Even cooler, I gave this to an intern and was able to teach it to an intern in a few weeks. And in the next week or two, we had this idea of writing a new schedule for a gem. And he was able to implement it in this very, very quickly. And he outperformed Kubla's by a lot, by 160% in a lot of cases. You can see how many cases we schmooed over here. He outperformed it in a lot of cases. This is a tech transfer that's still ongoing with Kubla's. We're getting this into Kubla's, we're getting this into CUDNN. And this was somehow written by an intern. That shouldn't be possible. This was not possible 4 or 5 years ago. We could not have written this in CUDA, been able to really quickly test a new crazy idea that we had, and be able to beat Kubla's this soundly. That is pretty impressive. But then my favorite bit is that with all this experience with tensors, I knew, and this is actually what this project is based on, is that all tensor contractions can be folded without any memory motion into a batched gem. And if you construct these multi-indices, which is actually just a layout, which I know how to manipulate now inside of this algebra, then I can make any tensor contraction look like a batched gem. And so if you do that inside of this project, then you have to add a couple of lines of code. You have to be a little bit careful with access patterns, this K dimension, the reduction dimension when it's a multi-index is kind of weird, and you can overstep memory bounds and stuff. So you change this line from a copy to a copy if, which knows about which elements of K are valid, and that's it. So you change a gem to a jet. This is a general tensor contraction. And I was able to beat Kublaw's, or CU tensor. I was able to beat CU tensor by a factor of 2x. Then, by not using these handwritten kernels that were based on Cutlass. And this is already integrated into CU tensor. So CU tensor is using this project named Qt in the backend already. But we're working on ways to publish Qt and make it more public and more tightly integrated into Cutlass, so that people can actually use this and hack on it themselves. If we can do this kind of thing with an intern, then you want to write some strange, skew of a matrix multiplication for your particular AI or DL problem, and you want it to run at 10 teraflops. Or I'm sorry, 10 gigaflops. Or no, this is 10 teraflops. And you want it to run at 10 teraflops on the newest GPU architecture. I think you should be able to do that, and I want to live in that world. So that has been my goal with this project.
Cris, I wanted to. Oh, okay.
Yeah, go ahead.
I wanted to warn you that we are at 10 minutes.
Yep, I'm just wrapping up now. Good.
Perfect.
So yeah, the goal with this most recent project is that I want to write functional code easily. And I want to avoid all of this bookkeeping disaster, which prevents even the writers from understanding this kind of code. And then I want to be able to optimize these kernels simply by changing the layouts of these threads and data and how these access patterns are happening. For that, I have a single representation of a layout, which is powerful enough to represent everything I need to represent. And I have a composition, which is a single operator that's used throughout this library and wrapped in clever ways. We were able to beat CU tensor. We were able to do hackable speed of light kernels. This StreamK implementation was written by an intern and able to beat it. We also used it with another intern to implement some sparse linear algebra prototypes, and we also beat CU sparse pretty easily with those, and be able to implement some really complicated algorithms very, very easily there. And I'm looking forward to spending a lot more time on this and getting it into the mainstream. And this is a bunch of stuff we didn't even get to cover. I love doing formal C++ software development, and I've done a lot of work with Jared and C++ standards. This direct H solver for backpropagation in AI was a fancy little thing that almost worked. Sparse multilinear algebra, I didn't get to talk about that much. And the next generation of GPUs, which I can't talk about, but I feel like I already have a very, very good successful story that I can tell there. So with that, I'll wrap up and answer any questions that anyone has.
Thank you very much, Cris. We can take few questions. We have time for a few questions. Maybe I'll get started. That I was curious about, but in general, this idea that you sort of went back to even FFTs and found a way to actually recast the process that formally didn't seem to be necessarily very efficient to start with, but with sort of development of new machine, this became now a real advantage. So I was wondering. I think that's a great story, great success story. And I imagine that these things can happen all the time. So I'm wondering how often you see these, especially for GPUs, given how different they are from other systems, that you've sort of seen sort of new, old algorithms or old ideas sort of be translated now into algorithms that are actually more and more efficient. Is there anything else that you can point to? I'm pretty sure, especially the students would appreciate sort of the idea that, it's good to go back to Euler at some point, or
yeah, there's a lot, and I think that was a big revolution even when I was still in ICME as a grad student, is that as computing gets more powerful and computing is free and memory motion is the cost of your algorithm, then we've been developing algorithms in the 90s and the aughts in the wrong way. By counting flops is the wrong way to develop an algorithm. And Now we've got to do all of that work over again, with the assumption that computing is free. And Jensen has this really amazing analogy, which is, imagine we could take transportation and make a trip from LA to New York take 10 minutes. That fundamentally changes the world. That factor of 10x or 100x, when you can take 10x or 100x in compute time, in travel time, in whatever, you change that entire field. You change a lot of things. And the world just starts functioning differently then. And that's true for computational mathematics as well. One of the reasons why I'm at Nvidia is because of these types of algorithms, where I know that in order to get some of the things that I want to work, in order to get them to work, I need the fastest computers in the world, because that's the only place where they will work. But in 10 or 20 years, that's going to be normal again. And so you can get way ahead of the game and invent and popularize completely new ways of doing things.
Very interesting.
And be successful doing it. Yep.
Maybe just a quick follow-up on this topic, but also something you mentioned at the very end, this idea of views of the data and layouts. Now, I sort of obviously see the value in using them, but from a practical perspective, behind the scenes, how complicated it is to keep all these views sort of updated and make sure that you are not conflicting, or that in a sense that you can really use them freely, meaning that you can define 10 views anyway, even if perhaps only 3 are the ones that are going to be useful. So yeah. How is the overhead of those in your setting, in your context?
I mean, as you can see, there is no overhead. This is generating assembly code, or GPU SAS code that is nearly identical to that in cuBLAS. It's simply wrapping it in a way that is more human understandable. And so yes, I've gone to great extents to make sure that there is absolutely no overhead, no compute overhead. In generating things and writing things this way. That said, yes, the idea is to write the complicated stuff once, and then have the entire system downstream figure out all the tough stuff, like the partitioning and the thread layouts and all the other things. And then you don't have to do that bookkeeping, and you can play around with what's important, which is the access patterns and vectorization and all of the things that are important for optimization, without having to rewrite the entire kernel. The entire kernel effectively rewrites itself and does all the bookkeeping code. Like I've said, passing this off to interns and seeing success stories with interns has been really, really rewarding. And it's honestly difficult to write incorrect matrix multiplications. That's not a lie. I just spent an afternoon last week getting an SOL Ampere kernel that I didn't have before, and I didn't see an incorrect version. I saw versions that performed poorly, but I was trying to optimize. But I did not see an incorrect matrix multiplication the entire day, and that was a really fun world to live in. So that was cool.
Very cool. Very cool. Okay. Well. Any questions from the audience? I don't see. Okay, I don't know if you can see the chat, but anyway, of your math skill set that you use day to day now, how much do you feel was learned on the job versus from ICME?
Yeah, so that's actually an interesting story too. So when I got to Harvard, when I was at ICME, I knew that I was interested in software and programming, and I wanted to learn, more formal styles and how do I write this grad student code in a way that's not a complete and utter disaster. I tried to take a bunch of CS courses when I was at ICME, and I knew that they weren't they were not thinking about it the right way. I didn't know I didn't know what the right way was, but I knew that these weren't them. When I got to Harvard, I wrote the class that I really wish I had taken at Stanford, and that's, yes. So in this postdoc professorship at Harvard, this class is where I learned the majority of a lot of this formal software development and changed the way I thought about software. And this is also the class that I took back to Stanford. When I moved back to the Bay Area, I taught this class for, I think, two years as an adjunct at Stanford. I think it's evolved significantly since then, so I don't think it's the same course anymore, but it might be fun to return and actually influence how that is. Because that's something that I look for in grad students and interns is yes, we can do amazing things, but I think it's really, really important how you think about software and how you approach it. And I like a very, very formal approach where if I can prove everything about my program and nothing can go wrong, then I'm in the right place. It's difficult to get there though. So yeah, so a lot of it did happen after ICME, and it took a long time to figure out some of the tools that I needed after ICME.
I would argue though that some of the linear algebra and fast multiple sort of background that you learned in ICME probably was useful, and
oh, yeah.
Especially some of the more recent work.
Oh yeah, and that's why this FFT project is still my absolute favorite all-time top project I've ever worked on, because it was the confluence of every field that I've ever had any kind of expertise in: physics, computational mathematics, because I did a lot of the performance analysis and correctness and error analysis and factorization, everything, low rank structure, algorithmic development, but also really high performance computing and really solid software development. So yeah, that's my all-time favorite project that has used every system that I have available to me. So.
Well, that's great. Well, I guess it's 5 p.m., so it's time to go. I want to thank you again, Cris. This was fantastic. I really appreciate you taking the time, and hopefully you can join us tomorrow at Expo, and you all in the audience. As you know, we have our research symposium coming up tomorrow morning. So thank you again, Cris, and I definitely look forward to get you again, involved and connected to ICME, as before. So.
Thanks. I would love that.
Okay, very good. Thank you. Thank you again.
Thanks for having me, Gianluca.
Thank you all.